Okay, so let's think about something really simple. A candle.
Right?
That thing you light, maybe for dinner, maybe the power is out. Seems basic. Fire, fuel, done.
Mm-hmm.
But what if, just by looking really closely at that candle burning, this thing we see all the time, what if that opens up like the whole universe, or at least the laws that run it?
That's exactly it. It's just an amazing idea from the source we're digging into today. It's a classic work, The Chemical History of a Candle by Michael Faraday.
Faraday.
Right.
Yeah.
Based on lectures he gave way back.
Yeah.
But the science, the observations, they're just timeless. Really foundational stuff.
So that's our mission then. For you listening, we're going to take this, everyday object and really unpack it using Faraday's insights.
What it's made of, how the fuel actually gets to the flame.
What even is the flame? Why is it bright? What comes out of it?
And believe it or not, how it connects to us, to our own bodies.
Wow. Okay, so it's a real deep dive, starting with just a candle.
Exactly.
Yeah.
So, where do we start? Let's look at the candle itself. What's it made of? Because it's not just one thing.
No, definitely not. Historically, it was quite different. You had things like tallow, animal fat, basically.
Ox fat, yeah. The source mentions Russian tallow specifically, often used for making dipped candles.
But then, science progressed. People got smarter about processing these things.
They did, chemically processing fats to make things like stearin, derived from fat, but cleaner, less greasy, made for a much better candle than just plain tallow. Balusiac gets a mention there.
So chemistry improving the candle. What else? Not just animal fat.
No, you had spermaceti from whales, beeswax, of course, both the yellow kind and the more refined white wax.
And paraffin. That sounds more modern.
Well, it was newer then. Faraday mentions it coming from Irish bogs, which is interesting, and even something called Japan wax as trade opened up.
Quite a range. And how are they made? Just dipping.
Dipping was common, yeah, but also molds. And Faraday makes this neat point. The molds were often conical, slightly tapered.
Why?
So when the candle cooled and, inevitably shrank a bit, it would just pop right out of the mold. Simple, clever design.
Huh. Makes sense. And wax candles often involved repeated dipping, right? Building up layers.
That's right. Layer upon layer on the wick. There's even this great little story about a candle found on the Royal George ship.
The one that sank.
Yeah. Way back in 1782, they found a candle over 50 years later, underwater all that time, cleaned it up, lit it.
And it burned.
Burned perfectly regularly. Shows how stable these materials can be.
Amazing. Okay, so materials, methods. They even mentioned fancy candles, like colored or fluted ones.
Yeah, decorative stuff. But Faraday makes a really sharp point here. Beauty isn't always utility, especially with candles.
What do you mean?
Those fluted candles, they look nice maybe, but they burn terribly. The shape interferes with the process.
Ah, okay. So the real beauty is in a candle that burns well.
Exactly. The beauty of the process working correctly. And a key part of that is how the top of the candle behaves. You get that little cup forming.
Right, the pool of melted wax at the top.
And that cup is crucial. It's formed because the rising hot air around the flame keeps the outer edges of the candle cool enough to stay solid. It creates a little container.
Okay, so the air current helps make the cup.
Yeah. But if you mess with that air current like with a draft or one of those badly designed fluted candles, the sidewall melts too quickly.
And then the wax runs down the side, guttering.
Exactly, guttering. And if too much melted fuel runs down, it can actually cool the base of the wick and put the flame out.
Huh. So the cup needs to stay intact. But how does the fuel in that cup get up into the flame? It's defying gravity.
Ah, well, this is where a really fundamental bit of physics comes in, capillary attraction.
Capillary attraction. Okay, sounds scientific.
It is, but you see it everywhere. It's basically liquids being drawn into narrow spaces. Faraday uses some brilliant examples.
Like what?
Like water wetting your finger. It climbs up slightly, sticks to you. That's adhesion related to this. Or a towel hanging over the edge of a basin.
Oh, yeah, it sucks the water up and over.
Precisely. It acts like a siphon because the water is drawn into the tiny fibers of the towel. He also shows liquids rising up porous things like salt columns or how a fine wire mesh can hold water.
Because the gaps are so small, the water sticks in them?
Exactly. Or even a piece of cane soaking up camphene fuel. The natural tubes in the cane act like a wick.
So the wick in the candle, the cotton fibers, they have tiny spaces.
Tiny channels, yes. And the melted wax, or tallow, is attracted to the cotton, and the wax molecules are attracted to each other. This mutual attraction pulls the liquid fuel up those channels.
Up into the hot part.
Right into the flame where it's hot enough to be turned into something else.
Amazing. Just physics pulling the fuel up.
Ah.
Okay, so the fuel arrives. what about the flame itself? It always looks like it's dancing.
It really is. It's not a fixed shape.
Yeah.
Faraday uses this great analogy of a snapdragon flower reacting when you touch it, those little flickers.
Yeah.
He says the tongues of flame you see, especially in a draft, aren't separate things, just the single flame rapidly changing shape because of the air currents. It all blurs together.
That's a cool way to think about it. But inside that flickering, there are different zones, right? Like the dark bit near the wick.
Yes, that dark inner zone is key. That's where the liquid fuel, drawn up by the wick, gets heated.
Okay.
Turns into a vapor there. But there's not enough air inside the flame right at that point for it to actually burn yet.
So it's fuel vapor, just waiting.
Exactly.
Mhm.
And Faraday demonstrates this so elegantly. He sticks a thin glass tube right into that dark part of the flame.
And what happens?
He draws off the unburnt wax vapor. You can see it coming out the other end of the tube. It's heavier than air, so it flows downwards.
Whoa.
And then, if you put a match to the end of that tube, poof, the vapor burns, completely separate from the main candle flame. He calls it laying on a candle.
So you can literally tap the fuel source before it burns. That clearly shows vapor production is separate from the burning.
Absolutely. Clear separation of zones. So the vapor forms, moves outwards, mixes with air, and then burns. But why is it bright? Burning doesn't always mean bright light.
Good point. Like a gas stove burner, it's hot, but not that bright.
Right. Faraday argues very convincingly that the brightness in luminous flames, like a candle's, comes from solid particles within the flame getting extremely hot.
Solids inside the flame.
Yeah. Think about heating a piece of metal, like a poker in a fire. It doesn't burn, but it glows red hot, then white hot.
Mm-hmm.
That's incandescence, heat making a solid luminous.
Okay.
Or think about burning something like zinc. It burns with a really bright light, and it produces these fluffy, solid particles of zinc oxide.
So back to the candle.
Yeah.
What are the solid particles?
It's carbon soot. Charcoal, basically. The wax vapor, which is made of carbon and hydrogen, breaks down in the intense heat near the center of the flame.
Right.
Before all the carbon can find oxygen to burn completely, some of those carbon atoms clump together into tiny, tiny solid particles.
Like microscopic bits of soot.
Exactly. And those solid particles get heated to white-hot incandescence by the surrounding burning gases. That's what you're seeing. That's the light.
No way. The brightness is literally tiny glowing bits of soot.
Essentially, yes. Before they themselves burn up higher in the flame, he shows this too, by piping smoke from camphor, which is very sooty, into a hydrogen flame.
Hydrogen burns almost invisibly, right?
Very faint flame. But when the carbon particles from the camphor smoke enter that hot hydrogen flame, they glow brightly. They become luminous just from the heat.
That really proves the point. Solid particles heated up.
And one more piece of evidence. Take a bright flame, like from coal gas, and give it more air. Blow on it or use a special burner cap.
What happens?
The flame becomes less bright, more blue, because with extra oxygen mixed in early, the carbon burns completely, very quickly.
Ah, so it doesn't get a chance to form those solid particles and glow first.
Exactly. The carbon still burns, releases heat, but you lose the light show. So that carbon, liberated from the fuel, is absolutely key for the candle's brightness.
Mind blown. Okay. So fuel gets up, turns to vapor, carbon particles form and glow, then everything burns. But what does it turn into? What are the products? You can't see them.
Mostly invisible, yeah. But they are there. One major product is water.
Water. Really? From burning wax?
Absolutely. H2O. You can easily collect it. Just hold something cold like a glass or a metal dish over the flame for a moment.
And you get condensation.
You'll see moisture forming.
Yeah.
That's water produced by the hydrogen in the fuel, combining with oxygen from the air.
And Faraday points out something amazing when you burn. Burn a pint of oil, and you get more than a pint of water out of it.
Yeah, it shows just how much hydrogen is locked up chemically in those fuels. And this water, it's the same stuff we drink, the same stuff that makes ice and steam.
Right, it changes state.
And Faraday loved showing those changes. Boiling water makes steam huge expansion. A cubic inch of water becomes like a cubic foot of steam. Enough force to rattle lids or
crush a can when the steam inside condenses back to water, creating a vacuum. I remember that experiment.
That's the one. And
Yeah.
the reverse. Freezing water into ice. It expands then too. That's why pipes burst, why ice floats.
It floats because it got bigger when it froze, so it's less dense.
Exactly. Takes up more space than the water it came from. And water isn't inert. It causes rust, reacts vigorously with things like potassium.
Okay, so water is product number one. What else? The carbon has to go somewhere.
It does. The carbon combines with oxygen to form the other main product,
Yeah.
carbonic acid. We usually call it carbon dioxide now, CO2.
Carbonic acid? How did Faraday show that was produced?
With the classic test. Lime water. Clear calcium hydroxide solution.
Right.
If you bubble the gases from the candle flame through lime water, or shake up gas collected from above the flame with lime water.
It goes cloudy, milky.
Precisely. That cloudiness is calcium carbonate chalk or limestone, basically formed by the reaction between the carbonic acid and the lime water. Ordinary air doesn't do that nearly as quickly.
So proof the candle makes carbonic acid. What's this gas like?
Well, first off, it doesn't burn. And it won't let other things burn in it. It extinguishes flames.
Puts them out.
Yeah. Faraday says it puts out the combustion of everything. It also has no smell, no taste. It's neutral, not acidic or alkaline to the senses. Doesn't dissolve much in water, though a little bit makes the water slightly acidic.
Okay, and it's heavy, right?
Very heavy. Much denser than air. He gives the numbers about 16 grains per pint versus maybe 10.5 for air.
And he showed this weight in really cool ways.
Oh, yeah. Like pouring the invisible gas from one container down into another that has a lit taper at the bottom.
And the taper goes out when the gas reaches it?
Exactly. Or lowering a candle down into a big jar filled with the gas that goes out when it hits that invisible layer.
It's like an invisible pool of heavy gas.
It is. He even showed you could float soap bubbles filled with air on top of it. Or pour it onto a balance and show it weighing down the scale.
Demonstrating its weight directly. Okay, so the candle burns wax, carbon and hydrogen, using oxygen from the air.
And produces water from the hydrogen and oxygen, and carbonic acid from the carbon and oxygen.
And the carbon part is what made the flame bright before it turned into carbonic acid gas.
Correct. He also shows this by burning pure carbon charcoal in pure oxygen. It glows intensely, sparks fly, but there's no real flame. And the product is carbonic acid. Pure carbon leaves no ash.
Unlike burning, say, lead.
Right. Burning lead makes solid lead oxide ash, which can pile up and smother the fire. Carbon's ash is a gas carbonic acid, which just mixes into the air.
Which is why carbon fuels work so well in fireplaces and furnaces. The waste product disperses.
Clever design by nature, or very convenient for us. And wood, coal, gas, they all contain carbon and produce carbonic acid too.
Now this leads to what you mentioned earlier, the really big connection.
Ah, yes. The analogy between the candle burning and the candle. Human respiration.
Our breathing is like a candle flame. How?
Well, think about the inputs and outputs. A candle uses fuel, wax tallow, and oxygen.
We use fuel, food, and oxygen from the air we breathe.
Okay.
The candle produces heat, water, and carbonic acid.
We produce heat, our body temperature.
And we exhale water vapor and carbonic acid.
Exactly. The chemistry is strikingly similar. Our food contains carbon, hydrogen, oxygen, just like the candle fuel or like sugar, which Faraday discusses. That fuel gets processed in our bodies.
And in the lungs.
Oxygen from the air we inhale combines with carbon derived from our food, not free carbon, but chemically available carbon. This reaction releases energy, which is our body heat, and produces carbonic acid.
Which we then breathe out, along with water vapor.
Just like the candle.
Yeah.
That exhaled air, rich in carbonic acid, can't support combustion. Put a candle in it, it goes out. And critically, it can't support respiration again either.
You can't live breathing your own exhaust.
No. But here's the beautiful part of the cycle. That carbonic acid we breathe out, our waste product.
Plants need it.
Yes. Plants take in carbonic acid from the atmosphere, use the carbon to build their structures, leaves, stems, everything, and they release oxygen as their waste product.
Which we need to breathe to burn our food. It's a perfect loop.
A stunningly elegant natural cycle. Animals breathe out CO2, plants breathe it in and release O2. Even fish do it, using oxygen dissolved in water and releasing CO2. It connects everything.
Makes you think differently about just breathing. Wow. Okay, one more curious thing from Faraday. Why do fuels like wax or gas just sit there? Why don't they burst into flame instantly in the air?
That's a great question he poses. Some things do react instantly, like that lead pyrophorus powder or finely divided iron expose them to air, and whoosh, they ignite.
But candle wax, coal gas from a pipe, gunpowder, they wait.
They wait for a trigger. They need to reach a specific temperature, the ignition temperature, before they'll start combining with oxygen rapidly enough to sustain combustion.
You need to apply a flame or a spark.
Right. The gas can stream out, mixing with air, perfectly capable of burning, but it won't, until you provide that initial energy boost to get the reaction going. Turn off the spark, the burning stops.
Unlike respiration, which is happening constantly in us at body temperature.
A key difference. Our bodies manage that chemical combination much more gently, continuously. The candle needs that kick to start. It's controlled potential energy.
All these deep ideas from a candle. Now, Faraday didn't only talk about candles in these lectures, did he? He sometimes used them as a jumping-off point.
He did.
Hmm.
He touches on other fascinating science, like the production and properties of platinum, for example. A bit of a detour, but interesting chemistry he was exploring.
Platinum, right. That really heavy, precious metal.
Very dense, very resistant. He talks about how they used to make it workable back then. Before they could easily melt it, they'd take platinum powder or sponge and heat it intensely while hammering it, basically forge welding the particles together, like blacksmith's weld iron.
Hard work. But then there was a newer method.
Yeah, DeVille's process, using much higher temperatures, often from an oxyhydrogen blowpipe, hot enough to actually melt platinum properly. They'd purify the ore, which often had things like iron mixed in, sometimes by melting it with lead and other materials to separate out impurities. Then, the challenge was getting the pure platinum out of the lead mixture.
How'd they do that?
By heating the platinum-lead alloy in a special crucible made of lime. Lime withstands incredible heat and doesn't conduct it away easily. They blast air over the molten metal.
And the air burns off the lead.
The oxygen combines with the lead, forming lead oxide, litharge, which melts and flows away or soaks into the lime crucible, leaving behind the much less reactive purified platinum.
Ingenious, high-temperature chemistry.
Definitely. He even contrasts platinum stability at high heat with silver, showing how silver vaporizes much more easily under intense heat, like from a voltaic battery. It's a glimpse into the advanced material science of his day.
Really shows the breadth of his work. Okay, so let's pull back. We started with this, super familiar object, a candle.
Yeah.
And following Faraday, we've seen it's this mini laboratory, revealing how materials behave, how liquids climb through wicks via capillary action.
How a flame is structured, with vapor forming inside and burning outside. How the light itself comes from glowing, hot, solid carbon.
And the invisible results, water and carbonic acid, which we tested for.
And then connecting that whole process, fuel plus oxygen yields water, carbonic acid, and heat directly to how our own bodies work, how we breathe.
Tying us into the grand cycle with plants, where our waste product is their essential food, and vice versa.
It really drives home Faraday's core message, doesn't it? The power of careful observation. Asking why about the simplest things can unlock incredibly deep understanding.
It really does. What's the biggest takeaway from you, having gone through this again?
For me, I think it's that profound interconnectedness. Seeing the very same chemical transformations in a simple flame and within ourselves, linking us to the entire ecosystem through something as basic as carbonic acid. It's humbling, really.
Yeah, I agree. And for me, maybe it's that idea of potential energy just waiting, the fuel needing that ignition point. It's not just chaos. There's this stored order waiting for the right condition. It makes you wonder.
Yeah. What else is like that?
Exactly. What other everyday things are holding these incredible scientific stories, these fundamental principles? If we just, stop and really look, it's something to think about next time you light a candle, or even just take a breath.